broadcast is now starting. All attendees are in listen-only mode.
Hello, this is George Schutz. Thank you for attending today's Measurement Basics webinar. I'm your presenter, George Schutz from Mahr Incorporated. I'm Director of Precision Gauges. I've been with the company for over 40 years, worked in all phases of dimensional gauges, and I'd like you to take a look at quality gauging tips articles in Modern Machine Shop, as I think this is a lot of the information that you'll find in today's webinar. If you have any questions about anything we talk about today, feel free to email me at george.schutz@mahr.com, and I'll respond and try and answer your questions. We have some objectives today. I think that's always important. We're going to try and understand what the measurement process is, to learn at the difference between measuring and gauging, to be aware of the performance capabilities of measuring and gauging instruments, and learn about some of the enemies of making precision measurements. We'll try and keep it light, and we'll try and keep it fun. We always talk about measuring and what the measuring process might be. I think measurement is more than just a number from a sensing device or a measuring instrument. Now, you can go out into your backyard and read your thermometer and see that it's 50 degrees Fahrenheit. Well, you've made a measurement, but really there's a lot more than that, and that's especially true when we talk about dimensional measurements. There's actually a logical sequence to the operation used to perform that measurement. That sequence is a process that consists of at least 5 different elements, and each one has its own influence. So I take a look at this picture here. This is a typical measuring process that's happening in a shop environment. How many elements of the measuring process can you identify? Let's see what we can find. The first one down the bottom there is the standard or the master. This could be a master ring, a master disc, a gauge block, some reference standard. The second part of the measuring process is the workpiece, the piece that we're actually trying to measure and find the dimension of. The third part of the process is the instrument, the gauge or the measuring device, what we're trying to use to measure our part. The fourth part is the person or the people making the measurement. They can have a very big impact on the measuring process. And the last part, the fifth part, is the environment. The environment's always around us. Again, this is probably the most critical part of the measuring process. So the measuring process is more than just a number. It's 5 different parts. And the best way to remember this is by an acronym, and I like to refer to it as SWIPE. And from the measuring and gauging business, we always can use this to help us find problems with a measurement result. Sometimes when it's not right and we think that there's something wrong with the gauge or the part or something, by using the SWIPE principle, we can learn where that measuring error might be coming from. Let's take a look at these 5 different parts and just understand how maybe they can contribute to the measuring process. Well, the standard is the master. It's the gauge block or the rings or the pins, whatever. And when we're making a measurement process, we want that standard to be clean. We like to have it the same material of the part that we're measuring. It should be the same temperature that the gauge is working at. Hopefully, the master is recently certified so that we know its size and form. It should be in good condition, no rust on it, no nicks, burrs, and so forth. And hopefully, it's made to a standard. Gauge blocks are made to a standard. Rings and discs are made to a standard so that we know the overall uniformity of the form and surface finish and so forth. The second part of the process is the workpiece. Again, it should be clean, same material, gauge in the master. Again, good condition, no burrs on it, temperature stable. We don't want to be measuring a hot part. And we should understand the form and finish and how they can affect the measuring process. We should also know about any special characteristics of the part. Is it a thin wall? Is it a compressible material? Those can influence the measuring process. Now here's an example of how geometry can affect the measured size. It's kind of important, especially when we have tighter tolerances, to know the form of the part when selecting the right gauging. In the top picture here, you can see that that's a round part. It's simulating a round part that has what we would say is an even number of lobes. It has basically a larger and a smaller diameter. Now, when we measure that part with a adjustable bore gauge or an air plug or a mechanical plug gauge, it's easy to see the difference between the major and the minor diameter. But if that part has an odd number of lobes, like in the lower condition there, a 2-point gauge is not going to measure that part correctly, because as the gauge rotates around that part, it always sees the same diameter. So often when a new part is being manufactured for the first time, it's very critical to take a form measurement of that part to understand what's going on, and that will help us ensure that we have a right gauge for that application. The next part of the measuring process is the instrument. I like to refer to this as being only 1/5 of the measuring process. That's because we get a lot of calls where a customer will tell me that their gauge is not working properly. Well, I sit back for a minute, talk about swipe, and usually we can find that maybe the gauge is working right, but there's something else going on. But gauges are a big part of the process. They should be large and strong enough and have enough mass to be a stable gauge platform. They should be mechanically sound with no long arms and overhangs and so forth. They should be tested for repeatability, have the proper resolution for the application. The operator should not have much influence on the measurement. Sometimes gauges are made to a standard. That's especially true when measuring compressible materials. And it should take into any account for part characteristics, like the form condition or a thin wall and so forth. That's all part of making a good measurement. Here's another example of how a gauge, which is perfectly good for one application, might not be the right one for another application. And this is showing an example of an air gauge, the picture on the left, compared to a mechanical bore gauge, the picture on the right. Air gauging is a great tool for very tight tolerances. It's fast, it's repeatable, little operator influence, and it's very accurate. Great tool for on the shop floor. With air, though, with an air gauge, it uses air back pressure to make that measurement. And there's a small jet there where the air passes through, has to build up a back pressure from the surface to provide its measurement. Well, when that surface is very rough, their air has to fill in those peaks and valleys on the surface. In reality, it can think that the measured surface is below the very top of those peaks. A mechanical plug gauge, for example, with its mechanical contact, is only going to ride on the peaks. So if we have a very rough part and we're trying to use an air gauge, there's going to be some concerns. So this is another example when you're trying to measure a very tight tolerance, you have to understand before the form, now we have to understand the surface finish of the part. It all comes down to providing the right gauge for the application. And then there's the people. The people are a very big part of the process I mentioned before. And some of these conditions here are, things you might think of in a precision measurement center, where people are working together usually in a back room in a big plant. They should be even temperament, working with each other very closely. They should be emotionally stable, take pride in their work. They have to be a perfectionist, because some of these standards that they're measuring might be used in parts that are life and death critical. So these can be very important things that they're doing. They have to have good judgment to make sure that if they see something wrong, that maybe they need to make that measurement over again. And they also have to have a good sense of humor about that, to realize that, well, maybe I just wasted 15 minutes and they have to do that measurement again. Well, you have to move on and make sure that they get it right. And you can see there's a lot of characteristics here of people that maybe there's some other industries where people who do that can move into a Gage lab type of person. And I think that people who might have worked in the Navy one time on a submarine probably have the right skills to be a great dimensional lab technician. They work in a room, a lot of people together, their jobs are very critical, it's probably a very close environment, so maybe they're getting some good life characteristics to be a dimensional lab technician. And finally, the last part of the measuring process is the environment. And the environment is probably the largest contributor to measuring errors, with dirt and grime and oil and vibration and humidity in the air. There's lots of sources of error with the environment. You can see on this picture on the left here how a lab room might have a 10-degree temperature change simply between the ceiling and the floor itself, with the air conditioner trying to move things around. You have a person generating heat. You have heat from the light. All these things are contributors to the environment. And when we're starting to measure submicron tolerances, the environment can be a very big contributor to measurement error. So by knowing this measuring process, we have a better understanding of each of the elements. We can find our biggest sources of errors. We're capable of documenting the performance of each one of those areas and maybe come up with some what we call uncertainties of where our measurement errors are. We can improve operator involvement, make sure that they're well trained and capable of using the machines. It helps us to troubleshoot questionable readings, to find out where our sources of errors are. And it helps to make the measuring instrument have the least influence on the measuring process. So remember SWIPE, and I think it'll solve a lot of your measuring errors that you come across. Now, I do it just as much as anybody else, and I tend to use measurement and gauging very interchangeably as we talk about things. And really, they are the same, but there is a distinct difference between them. Let's talk about that. Measuring, I think, is a process of determining the dimension of a part by comparison with a standard. So it's kind of a direct reading instrument. Gauging, on the other hand, is a process of determining whether the dimension of a part is smaller or larger than a standard. I would say that's an indirect reading instrument. So measuring instruments use an internal scale, and we use that to measure the part, compare it to that internal standard. The scale is the internal standard. So the scale is built in because it's very versatile. It can measure a large range of dimensions, but it's relatively slow because it requires more skill by the user for accurate measurements. And because there's more operator involvement, misalignment of the tool and so forth, they generally have greater measurement uncertainties. So these are some basic measuring instruments where the scale is built in. You have scales themselves, micrometers, calipers, height gauges. Laboratory measuring machines are measurement instruments, universal measuring machines, and there's shop floor length measurement machines. All have great versatility and all with very different levels of accuracy and performance. Now, gauging, like these instruments, like we said before, determine whether a dimension of a part is smaller or larger than the standard. So in this case, the gauge has external standards. You can see the master ring down by the gauge on the lower right of the picture here. But they tend to be faster and more accurate than measuring hand tools because it's a little more dedicated to the process. And gauging instruments can be divided into various levels of performance. I think we can talk about them as being good, better, and best, and we'll look at some of those. So the first level of a gauge is we call it an adjustable variable gauge, kind of like an adjustable bore gauge. It's adjusted to a specific size. It has lots of adjustable range, but you can limit it to a very small measuring range. They provide, again, actual deviations compared to a master, but in this case, the operator has to sweep the part to capture the size that he's trying to measure. Therefore, it takes some operator skill, but with the right practice and experience, they can be fast and easy to use. They usually have only one master for the size we're going to measure, the nominal master. And these can have not a very large investment, but they're gauges that have been around for decades when taken care of properly. And by measuring multiple diameters on a dimension, you can get a general idea about what the form or process trend might be and help diagnose manufacturing issues. Here's again some adjustable variable gauge examples, adjustable bore gauges, adjustable ID/OD gauges. All these require some operator involvement, but they have long adjustable range, but a very precise measuring range. Now we can improve that a little bit by having an adjustable variable gauge, but now we're going to add a reference to it. So in case of the snap gauge, the upper anvil can be adjusted to accommodate a lot of sizes. We have a lower anvil as our reference, but we're going to add a backstop to it now. So what's that take away? It takes away one of the motions that the operator had to deal with previously with the adjustable bore gauge. So again, they're adjusted to a specific size. They incorporate a reference lock to help position or really snap or lock the part into a repeatable place on the measurement. They take a little less operator skill. They can be fast and easy to use. Again, limited measuring range, a lot of adjustable range. They again provide actual deviations, require a single master, and again, you can use these for years and years, and they can help you in the manufacturing process. Here's some examples of adjustable variable gauges, whether it be snap gauges, bench ID/OD gauges. Any bench stand can be with a backstop, can be a variable gauge with a reference. And now we move into our fixed variable gauges. These are gauges which can give you some deviations, thus they are variable gauges, but they're more made to a specific size. These are the most accurate types of variable gauges. They provide actual deviations, the very least operator influence because They can only go into the part one way. There's no slop in there. You get a reading instantaneously, and it's very accurate. Thus, it's very fast to use. It's good for one size. Because it's the most accurate, it has the highest resolutions down to submicrons. Therefore, you can learn a lot about the form, process trends, and help diagnose manufacturing instruments. Again, it's a little bit more, it's probably the most costly per measurement available, but again, you're getting the best results, the fastest results, and the easiest to use. So the investment is well worth it. And most of the air gauging, the Metron plugs that we manufacture and so forth require only a single nominal master. So here's some examples of fixed variable gauges, mechanical plug gauges, air gauging. They're all made specifically for a certain size and a certain tolerance, but give you the fastest and best results. Then we can get into some hybrids, maybe some gauges that have relatively long range, but you have to be able to use some care with them. Tri-bore gauges have a lot of measuring range, but again, this is a kind of a hybrid, but in the right application, they can give you some very good results. So I like to think of these gauges in good, better, and best, and so forth. So we said that hand tools, which are measuring instruments, they have lots of versatility, but they lack speed because the operator has to bring them into contact, adjust them with their influence to get a good reading. So it's not that easy for the operator to use, and generally the performance of hand tools is not as good as some of the variable gauges. Variable gauges get better from the adjustable, then to the reference, and then the fixed variable gauge. But the fixed variable gauge is giving us the best performance, but again, the least versatility. So which one do you want to use? Well, there's lots of factors for choosing the right measuring or gauging instrument. What the accuracy, what the tolerance is, what cost, what the time and throughput needs to be, how easy it for the operator to use. Is there any maintenance costs we have to worry about? Is the part going to be clean when we make the measurement? Do we want a portable or a bench type of a gauging system? And of course, for tight tolerances, the workpiece form and finish is very critical. So those are all things that have to be considered when we're going to start making a gauging solution. Now, once we've chosen the gauge, there's enemies out there. There are enemies of precision gauging, and really it's a war out on the shop floor out there. And the enemy is trying to steal the microns and rob us of our best gauging performance. And I like to go through some of these things that cause us to lose microns, and maybe by knowing them, we can go ahead and eliminate them and prevent them from stealing those microns from us. Wear is a big enemy. One of the most common things as we see is worn contact points. You know, sometimes the gauges are measuring millions and millions of parts over the years, and they're not looked at very closely to see how things are wearing on them. And we want to make sure that we don't have worn contact, chipped contacts, parts are put only partially underneath the contact, and it doesn't take much more than a daily look by a user sometimes before they can start noticing some wear conditions. So we also want to keep the point that we want to push the part completely under the contact point. And if we don't do that properly, we can get some pretty significant issues. So wear is a key part of any gauging operation, whether it be a measuring hand tool or a variable type gauge. And it doesn't happen too much today, but we still see cases where masters are not the same shape or form as the part we're trying to measure. It's always good when you're trying to measure a round shaft or a part such as that to have a round disc as the master. That way, any wear that we see in the anvils is going to be transferred to both the master and the part. If we're going to be mastering the gauge with a gauge block and trying to measure a round part, well, there's apt to be an offset because any wear that we're going to see is going to be shown in the anvil and it's going to be part of our measuring errors. Dirt is a big contributor and one that can steal our measurements. And this is a very great advertising picture because we advertise our calipers and lots of our other gauges as being IP67 rated, which means that they're resistant to liquids and dirt. And it's great to show that we can make measurements with water splashing all around. That's really not the way we want to make a measurement. When we want to make a measurement, we want to make sure that the part is dry, that the gauge has also been wiped off and clean, and we have good measuring surfaces to make our measurements with. So while a gauge can be resistant to liquids and dirt, we don't want to measure under these conditions. Looseness is a big enemy of measurement. I want to make sure that we check all adjustment points to be sure that they're secure. So you can see that this is a simple bench stand here. There's probably millions of these in the shops around the country. And look at all these adjustment points we have. We have a post that's attached to a base, and we have an arm attached to the post, and there's a fine adjustment on there, and that indicator is attached to the fine adjustment, and there's a contact point. And any one of those can become loose and influence our measurements. So again, it's good daily practice to make sure that the gauge is tight and also it's clean before we start making a measurement. Deflection is another enemy that we see sometimes. Is the gauge robust enough for the application? Here's a case of a stand which has a pretty long overhang on it, and maybe the arm isn't robust enough to support the weight of the indicator, or any vibration that's coming through the stand it's on might get magnified and show up in variation as the indicator. So make sure that the gauge is robust enough for the application. And even with a caliper or micrometer sometimes, some of them, again, because they're influenced by the operator, not every operator has the same gauging force that is used with that instrument. So a person with a pretty strong thumb might be deflecting the instrument and causing a little offset in the readings. So deflection is built into everything, but you can control that by knowing the forces and building a good, stable gauging station. Gaging pressure is something that we might want to consider. What effect does the force have on the measurement? Well, if we have a very thin wall or a compressible material, it can deflect the part and influence the measuring result. For compressible materials, for example, there are standards out there that says we have to have a certain weight, a certain anvil or flat anvil, which a certain size that's used to be measured. So that way that part can be measured at multiple locations under the same examples of gauging to get the same results. So it's important to understand and make that part of the measuring process. The environment is the biggest contributor. We talked about that a little bit previously. There's lots of thermal sources of error, from the radiant heat from the lights, from conductive hands touching the pieces, convention drafts, and so forth, room temperature gradients. When you're measuring the submicrons, the environment can be a very big contributor, especially temperature. And vibration. Vibration can be a big problem, especially submicron measurement, and especially when making surface finish measurements, because sometimes you can't tell the difference between a surface finish trace and the vibrations that are coming from outside sources, whether it be internal, external traffic, radios, machines. They all may be interpreted as part of the measurement. And one way to look for this is just not make the stylus on the surface finish gauge move. Just let it sit there and observe the results. And hopefully you don't see much of a signal coming through at that point, and you can be sure that vibration is not making your measurement to process not be right. There's gauge geometry errors. We want to make sure that the gauge is robust, but we also want to make sure that it's square and there's no sine or cosine errors in our measuring process. So for a long-range measuring stand, it's important to have the probe or the measuring point and instrument be square with the reference surface that we're using and making our measurement against. The same thing applies to contacts or anvils. They need to be parallel so that we can put a part on either side of the anvil. Anywhere underneath that, they're parallel enough for us to get the same results. Again, that's a gauge geometry error that we might be looking at here. We talked before about the part geometry errors. This is another one that, again, can steal accuracy from our measuring process, and it's all the pure result of the part, and it can influence and demand what gauge needs to be used with that measuring process. And approximation is the last one. There's lots of ways that approximation can influence us. Sometimes the gauge does not, and an analog gauge like this here, does not have the proper resolution for the tolerance that we're trying to choose. A too coarse resolution can take up too much of the tolerance, and a too fine resolution can make the gauge too sensitive and trying to count between grads or parts of a grad, and it just makes it very difficult for the user to make that gauge, and sometimes can get a bad reading because of that. Or if the gauge is not being used straight on and the operator is reading it from the side and the grads are too small, you can get a parallax error. Again, it's all from just reading the indicator right and trying to guess at what the grads are saying. Approximation could be a big part of a measuring process. But once you understand all those things, there are some things that you can do to make sure that you get the most reliable results. With any gauging operation, we talk about gauges now and measuring tools. It's good to bring back a caliper back to its contact or back to zero every time to make sure that nothing has changed with the micrometer. Or it's good to put the gauge standard, the master ring or disc, onto the variable gauge and re-zero it, because you might get some offsets over time, temperature changes, dirt, and so forth. It's critical to re-zero occasionally and do that throughout the day. Again, at the start of the day, during the day, and at the end of the day, clean any dirt off the gauge, off the workpiece, constantly trying to battle dirt and get it off the gauges. Even letting a gauge sit overnight. You might clean it before you go home at night. You come back in the morning. There's a good chance that there's a thin film of oil or dirt or dust on that gauge that should be wiped off and re-zeroed before you start making your daily measurements. Make sure that the master and the workpiece and the part are all as close to the same temperature as possible. As you know, different materials expand at different rates because of temperature. Trying to keep those as close to possible. And also make sure that your masters and instruments are under calibration controls and certifications are up to date. It's becoming very critical to document the measuring process. That includes documenting the gauge, documenting the masters, and making sure that the right gauge was used to make the measurement on that part. All those things are starting to be controlled and documented today. And again, every day you should just make it a regular routine to inspect the gauge for wear, loose components, to ensure that we're doing our best to keep the enemy out of our gauging process. So I think by understanding and knowing the enemies of precision gauges, we have a chance to beat that away and learn what our measuring process is and understand the reasons for what the measuring and gauging and which one to choose is. We've seen lots of ways of making measurements and what questions to get the best gauge for the application. And we have to try and find a way to fight and keep our measuring process at its peak performance. So by knowing the enemy, we can defeat it. I often like to end with a little bit of thought here. This is a little saying that has been passed down. It says, when you can measure what you are speaking about and express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. And what we're trying to say here is that measuring and gauging is a common language to us all. We have to be able to understand it, what's behind it, know its measuring process. And once we understand all those things, we can ensure that we're getting the best results. But I have to just say that at the end here that we should have lots of reasons why we consider Mahr for our gauging needs and for your gauging needs. I think Mahr has lots of experience. We have lots of application know-how. We as a manufacturing company can build in the accuracy because we know metrology and we know measuring. We know accuracy since we not only make the gauge, and we also make the gauges to measure the masters. So we have the abilities to understand and control and know what the measuring process is. And I think we have very good technical support. You can call us, Mahr's in business. We answer the phone, and we're here to support you. So with that, I'd like to thank you for the interest in this webinar and Mahr's products. You can reach us anytime via email at info@mahr.com. You can contact me directly at george.schutz@mahr.com. After the webinar is completed, we're going to send you a follow-up email where the webinar will be sent to you, and feel free to pass this around if you felt it's worth it. And I hope by understanding the measuring process of swipe, you'll remember what the gauging errors can come from in the future. So thank you for your attendance. Hope you're all well, and have a great day.